Okay, good. So welcome everyone, and yeah, today we have Sam Gunn speaking. Sam's a PhD student here at Berkeley, and you might know him, of course, from the famous Aronson Gunn paper, which he wrote as an undergrad. But since then, you know, he's already been doing a lot of very interesting work. Of various kinds, including committing to quantum states. And then this paper that he's going to talk about today, the work that he's going to talk about today is, I think it's really very interesting work, solving a major question in quantum error correcting codes. But what's very interesting about it is it's a purely student paper, Sam and Tiago and Luis. So looking forward to the talk, Sam. Please.
Yeah, thanks, Umesh. I'm Sam. I'm going to talk a little bit about some interesting aspects of approximate quantum error correcting codes. So first, let's just talk about what do we mean by error correction and by approximate error correction. So the idea is we're going to have some message row, which could either be classical or quantum, but for this talk, of course, it's usually going to be a quantum state. And we want to encode it into some code word, which is going to be, a larger string. And then some errors might happen to it. So we're going to imagine sending this code word across some noisy channel where some errors happen according to some error model. And then we want to be able to decode it back to the original message. Okay, so there's sort of two extrema models of errors that we could consider. So at one end, there's erasure errors. So this is where a few of the registers or the symbols basically just drop out of your code word, and then the decoding algorithm should get to see which ones disappeared. So as in know which ones disappeared, and then the decoding algorithm can just decode from the remaining registers. Okay, so this is sort of one model of errors. And then sort of at the other extreme, we could imagine an adversary who gets to go and access some limited number of registers of the code word and then do whatever they want to them. So the adversary can tamper them however they want with these registers however they want, and potentially even in an computationally unbounded way. And here we're not going to assume that the decoding algorithm gets to even know which registers the adversary corrupted. Okay, so these are sort of two basic models of errors. And the usual notion of that we require from our error correcting codes is that we can exactly recover the message. So even after the adversary tampers with some bounded number of registers, we should be able to perfectly recover the message that we started with. But in this talk, we're going to be more interested, or we're going to be focused on what we can do with approximate error correction, which is now we're only going to require the decoding algorithm to recover the message up to some small error, say epsilon. So in particular, we're going to really want epsilon to be exponentially small, so that you would never notice that you weren't perfectly recovering your messages. It's as if you just did them, perfectly. Yeah. So another thing that we want our symbols or registers to have constant size. So these black circles represent, the pieces of the physical system. So for example, maybe bits on your computer or qubits or qdits. And the reason behind why we want them to have constant size is that you can imagine, you want to be able to send these messages over some channel, and you have to have some physical implementation of your channel, and you don't want the physical system that you're using to have to change along with the file size of the thing that you want to send, or the size of the state that you want to send. So so you don't want your symbols to have to for example, become really large as you get a large file. And then finally, we're going to be interested in getting good rates. So the rate is just the ratio of the number of symbols in the message to the number of symbols in the code word. So if you have a high rate, it means that it's like an efficient code, meaning that, for every every register that I send over the channel, I'm, sending a lot of information. Okay. So these sort of two error models that we talked about, erasures and adversarial errors, are sort of captured by two parameters in classical code, or sorry, for codes called the distance and decoding radius. So the distance is the number of erasures that you can tolerate, and the decoding radius is the number of adversarial errors you can tolerate. So there's a picture for this that explains these words in the classical setting, at least, where you could imagine all of these blue dots are like classical code words and living in some space where the metric is like the Hamming distance. So the distance is going to be the minimum distance between any two code words, and the decoding radius is like the maximum amount that you can perturb from a code word and then still be able to go back, this decoding algorithm should still be able to uniquely figure out which code word you came from. So again, all in Hamming distance. So that's sort of where these terms decoding radius and distance come from. So here's just operationally, we're going to sort of use these in the green box, where distance is the number of erasures and decoding radius is the number of errors. And it turns out these equivalents, these notions are the same. At least for decoding radius, I think it should be clear. Okay, it's a fact that for classical error correcting codes, the decoding radius is always at most half the distance. So you can sort of see that from the picture. And turns out this is also true for exact quantum error correcting codes. And I'll try to sketch a proof of this in a few slides, like an outline of a proof of this. So our result is that we show that there exists approximate quantum codes where the decoding radius actually is all the way up to almost the distance for all rates and with a constant alphabet. So still in the setting of the previous slide. Okay, so let's get some more background and talk about our result in a little more detail. So first, there's like one basic upper bound on how well you can build a code called a quantum code called the quantum singleton bound. So this says that no quantum error correcting code of rate r can correct more than 1 minus r over 2 fraction of erasures. So for example, if you set r really small, like r equals 0, then this is saying that no error correcting code can correct more than half fraction of erasures. So this follows from just like the no cloning theorem, right? If you could correct from half of your erasures, that means that you could, take your message, encode it in the code word, and then decode the message completely from each half separately and get 2 copies of it. Okay, so in fact, this more general thing this more general bound, the quantum singleton bound holding for all r, follows from sort of similar reasoning. So let's see that now. So suppose that you have a code with distance d, meaning that it can handle d minus 1 erasures. So let's try to clone it. Let's do our best at cloning it. And we'll get a bound out of the fact that we can't clone it. So first, let's encode it into our code word. And now let's take some d minus 1 registers of our code word, and then let's like set them aside and take them over here. So now in this first code word, we still have all but d minus 1 of the registers. So because we're assuming the code has distance d, that means we can completely decode the message from this part alone. Okay, but then now we're trying to clone it, but this bottom part doesn't actually have enough registers to clone we don't have all but d minus 1 of the registers. So what do? Well, we just guess the remaining ones. So that's these yellow ones. Let's just say that you just like randomly guess these remaining registers, and then just try to decode this anyway, even though we guessed part of the code. So the number of registers we had to guess is going to be this, n minus 2 d minus 1. And basically, because we had a message of length k, we shouldn't have any way to convert the problem of guessing the message of length k into a problem of guessing fewer registers. So because of this, the size of the message should be at most the number of registers we had to guess. So I just wrote that out here. So that's just k at most, n minus at most the number of yellow registers that we had to guess for our code. Okay, and then just rearranging this equation and then dividing by n gives you the quantum singleton bound exactly. Okay, so also, as you can kind of see from that argument, there's nothing about the exactness of the codes that we use. So similar arguments extends to the approximate setting where we can show a robust quantum singleton bound. So robust quantum singleton bound just says that even if you allow like an epsilon amount of error in your code, then then the singleton bound can only be violated by like some small amount depending on epsilon. So technically, like we couldn't find this in the literature anyway. So in order to show like tightness of our rails, we had to prove it, but it's pretty much an extension of the existing arguments. So okay, so then for the second part, I told you that there's a relationship between the decoding radius and the distance, at least for exact codes. So this is for exact quantum codes and also classical codes. So we said that the decoding radius is almost half the distance. So in this slide, let me try to give you like a super high level sketch of the argument for how this goes. So what we want to show is that if you have decoding radius r, meaning you can correct from r adversarial errors, then we want to show that your distance has to be at least 2r. Okay, so the way that we see that is if you're assume we have some code with decoding radius r, then for any two encodings psi and phi of orthogonal messages, an adversary acting on r registers alone shouldn't be able to sort of make sort of equivocate between these. They shouldn't be able to make these two things, these two orthogonal messages look the same, or even look at all indistinguishable. So here I've just written that down, what it means mathematically. So if you say you start out with a state psi, and the adversary applies some operation v of weight r to psi, and then some other operation w to phi, then these states should still be orthogonal. The resulting states should still be orthogonal. So now if you take some unitary acting on 2r registers, you can decompose it into a sum of exponentially many tensor products of registers acting on r registers each, of two operations acting on r registers each. And by this equation up here, this has to be 0. So in roughly, this means that losing 2r registers doesn't remove any information about your message. So so this is super high level, but the main point is that this argument went by writing this unitary in terms of like a sum of exponentially many terms, and we really use the fact that they were all 0. So this is not going to extend to approximate codes, because as soon as you allow any notion of approximation, then you're not going to get all these terms to be 0. Even if each of these terms is exponentially small, the sum could still be large. So basically, this inequality that decoding radius is almost half the distance is just not going to hold in the approximate case. Okay, so now with these upper bounds, let's look at how our result compares to these upper bounds. So for the bounds that we just saw, this quantum column right here, which says that the distance is at most 1 minus r over 2, that's the quantum singleton bound. And then by applying this bound from the previous side, we can see that that the decoding radius is at most half of that. Okay. And then the classical singleton bound is like half as bad. So that's the classical column. So now what we're going to see is, so in the approximate quantum setting, as I said before, the robust quantum singleton bound still applies. So this first row is still going to hold. We still have that the distance is at most 1 minus r over 2. But now this second column, we don't have any better bound on it than that. All we know is that the decoding radius is at most the distance. So namely, an adversary could always just erase the registers they're given. So you can't tolerate more adversarial errors than you have distance. And then the interesting thing that we show is that this bound is actually tight. So we're going to show that we're going to construct codes that have decoding radius all the way approaching the quantum singleton bound. So all of these in the right column are all up to small additive factors. Okay, and moreover, our codes are going to have constant alphabet and inverse exponential error. So this is still in the setting that I described early on. We're interested. So one thing that's maybe kind of surprising is that this same phenomenon can't happen classically. So if you chose a small rate, then you can get classical codes which have distance like almost the entire code. So namely, you could have you could encode your message into some code word, delete almost the entire code word, and then you could still recover the message uniquely from whatever's the small amount that's left. But you can't hope to do the same thing with decoding radius. So now, if you don't erase the registers, but if an adversary were to tamper with almost all the registers, then they could always just replace whatever registers they have with like a valid encoding of some fresh message, and you would never notice the difference. So so you're never going to get classical decoding radius all the way up to the distance. Yeah. So okay, and in fact, this is sort of motivation behind list decoding classically, which is to get codes which in some sense have decoding radius all the way up to the distance. Okay, so this is our result again, but a little more formally. So for any like constant slack, so for any constant slack parameter gamma and any rate r, we're going to construct codes with rate r, decoding radius gamma off of the singleton bound, and inverse exponential error in constant alphabet, where the alphabet's going to grow with the slack parameter, which how much slack you want off of the singleton bound. So compared to previous work, this work of Crapeau, Gottesman, and Smith in 2005 sort of handled the gamma equals 0 and r about, or gamma approximately 0 and r approximately 0 case. So they show that you can have codes where the decoding radius is all the way up to basically a half, but they're going to have exponential alphabet. Yeah. So in other words, like the size of the registers that you need to send has to grow like very like linearly with the size of the messages that you want to encode. Okay, and then another work of Leung and Smith talk about the binary alphabet case. So they talk about a similar question, but their algorithm is going to have inefficient decoding. So they're going to describe, and they're also not going to reach the singleton bound because they only handle binary alphabets, and you can't hope to get to the singleton bound with binary alphabets. Yeah. So one second. Okay. So now let me talk a little bit about our techniques. Okay. So one of the main ideas behind our construction is list decoding. So let me describe what list decoding is, at least in the classical case first. So if you take so in error correction, you have some code word X, and then some error gets applied to it, and then you want to be able to decode it to normally you want to decode back to X. But for list decoding, we're going to say that you're just going to output your decoding algorithm just has to output a list of L possible code words, and we just require that that the true code word is in the list. So and then in order for it to be a good list decoding algorithm, you want L to be like polynomial. So you want there to be not like huge lists. And then yeah. So a little bit more formally, a code is delta L list decodable if for all corrupted code words, there's at most L possible decodings within, you know, the specified distance delta. Sorry. Okay. So Guruswami and Rudra showed in 2005 that there exist classical codes that are list decodable from errors all the way up to almost to the classical singleton bound of 1 minus r. So while you can't hope to uniquely recover your message from adversarial errors on almost the entire code word, you can hope to list decode it, to output a list that contains your message. Okay. So naturally, we're going to have to think about sort of a quantum version of list decoding. So quantum list decoding was introduced by Leung and Smith in 2008. I mentioned this work earlier. And then we use a slightly different definition, but it's kind of the same idea. We don't expect to be able to produce the list of decoded states because that would sort of seem to violate some sort of no cloning intuition. But instead, what we're going to do is we're going to produce a list of possible errors that could have happened. So a list of classical descriptions of errors that could have happened to our code word. Okay, so formally, we say that a quantum code is delta L list decodable if for all low weight errors, the decoding procedure produces a list of the possible errors that could have happened. So maybe you could imagine like measuring the stabilizer or measuring the syndrome of a code word, and then classically from the syndrome, classically computing the list of possible corrections. And then you want that there's a small list which includes the real correction. Okay, so now with quantum list decoding in hand, we can start to talk about how we construct our approximate codes. The first step is we're going to authenticate our message with some sort of authentication algorithm. So that means we're going to sample random keys K and then authenticate the message using K. And what authentication is going to do is it's going to allow us to detect errors if they happen on the authenticated message. So as long as the keys that we use are kept hidden from the error channel, our authenticator is going to like sort of flag errors for us. Okay, then we're going to combine. Then after we authenticate, we're going to encode the message in a list decodable.
I'm sorry,
yeah.
Sam. Just to go back to the authentication. So the authentication will only tell you that the message is unchanged or whether some error happened. It won't identify an error for you.
Yes,
right?
It won't identify an error. Yes. Oh, did I? If I said that, that was a mistake. Yeah, sorry. So the authenticator will just tell you whether an error happens or not, right? Yeah. Okay. Thanks, Umesh. So after we authenticate, we're going to encode the authenticated message into our list decodable code, and then and this is kind of a common technique classically to boost list decoding to something to unique decoding, where you authenticate and then you encode in list decodable code, because now whenever you prepare this list, you can sort of sieve the list and figure out which element in the list is the real message, right? Okay. Of course, the issue is that now you have these keys laying around. Authentication requires you to send these keys, to know what the keys are, to check the authentication as well. So how do we get these keys to the recipient without getting the channel without like accidentally giving them to the channel, to the adversarial channel, the error channel? Well, we use this thing called robust secret sharing. So it's a totally classical concept. And essentially what it does is exactly what we want. It's like a version of a classical, like a randomized classical error correcting code, where it also not only does it let you recover the keys, it also keeps them secret from any error channel that's only given a bounded number of the registers. So we're going to write it down like we're going to robust secret share our keys, and then we're going to sort of append them on register by register to the quantum list decoded encoded message. So our registers are going to increase by like a constant factor, but it's all going to be okay. These robust secret sharing symbols we're going to be able to choose them to be relatively small. So okay. So in a little bit more detail, what we mean by quantum authentication is called purity testing codes. So it's not quite the normal notion of quantum authentication, but it's related. So what we want is that for any error E that happens, the probability that the error is an undetectable error on the authenticated message is at most alpha, for some small alpha. Okay, in these, so basically, if any error happens to the authenticated message, then even if the error is high weight, then we'll pick it up, we'll observe it, as long as we have the correct keys. Okay, so these are known to exist, good constructions, and yeah, we just have to make sure the adversary doesn't see the keys. So okay, so then the other ingredient, the robust secret sharing scheme, is a completely classical object, which has sort of two requirements. So first, there's robustness, which says that you can recover the message with high probability. So here, it's kind of the same setting as error correction, where you encode, an adversary acts on some registers, and then you decode. But in addition to this robustness that you can recover the message, we want secrecy. So the message should be completely random, conditioned on the view of the adversary, of any adversary given only a bounded number of the registers. So this result of Kramer, Damgaard, Dotling, Ferret, and Spinney from Crypto 2015 says that there exists really good, robust secret sharing schemes that are going to be more than good enough for our purposes. So yeah, I won't get into these parameters, but they'll be good enough. So we're turning to our construction. Now, once we have a good authentication algorithm, a good robust secret sharing scheme, and a good quantum list decodable code, we can stick them all together in this way, and we'll get a good approximate quantum error correcting code. So here, if the authenticator has small error, has like exponentially small error alpha, and the secret sharing scheme has exponentially small error beta, and the lists are only polynomially large, then we'll have an exponentially good, exponentially small error in our approximate quantum error correcting code with unique decoding. Okay, so the remaining part, prior works handled, existing techniques handle the authentication and the secret sharing part. So the only thing we have to do is come up with a good quantum list decodable code. Okay, so in order to do that, we're going to heavily rely on this sort of classical old construction of quantum error correcting codes called CSS codes, after Calder-Bank-Shor-Stein. So what these do is, given two linear classical codes, C1 and C2, which are going to have to satisfy some certain properties related to each other that we don't need to get into.
I'm sorry,
Yeah.
Sam. Could you say what are the conditions you need from the list decoding? Because you said, well, there's already existing quantum list decodable code. So why do you need new ones? And what parameters are you looking for?
Yeah, so we want parameters reaching the quantum singleton bound. So we want so these are the parameters that we want. Basically, if we have a list decodable code which has decoding radius all the way up to here, which has like list decoding radius all the way up to the quantum singleton bound, then the sort of like wrapper that I described just a minute ago is going to let us convert this into a unique decoding code. So yes, yeah, great question. Basically we want list decoding up to so in some sense sort of the same thing we had classically, right? List decoding takes you from unique decoding radius to distance. Quantum list decoding is also going to take us from
So is it correct that if you wanted to, you could also say what you're doing is achieving list decoding up to this radius, this bound, and then there's a icing on the cake, which is actually the final result, which is getting an actual error correcting code also.
Yeah, exactly. Yeah, which I think is kind of surprising because classically it's like you need list decoding to go between these. Quantumly, we're going to use list decoding in order to construct these codes, but then somehow at the end they're going to not be necessary anymore. Yeah. Okay. So very good questions. Oh yeah, and you asked about, okay, prior works do codes. So the only prior works that construct list decodable codes is this Leung and Smith paper, where they construct list decodable codes for binary alphabets. But the main problems are, one, that there's no efficient algorithm for actually decoding them. So just kind of like an information theoretically existence thing. And then also, since they're only over binary alphabets, they won't actually reach this quantum singleton bound. Okay. So, okay, so yeah, so I was talking about CSS codes. So CSS construction is some way to take two classical codes and sort of like stitch them together and make one quantum code. It's going to inherit a lot of the properties of the classical codes. Okay, so then really the important thing about CSS codes that we need is that correcting errors is a very simple operation that goes as follows. So first, you correct errors on like one of the codes, and then you're going to apply the quantum Fourier transform separately to each register, and then you're going to correct errors on the other code. So it's sort of like there will be like regular standard basis errors on one code, and then phase errors in the other code, and the Q of 2 will let you go between them so you can correct both. Okay, and then it's the theorem of Calderman ensure that that if C1 and the dual of C2 both correct our errors, then the CSS composition corrects our errors. So really, the important takeaway is just that if C1 and C2 are good codes, then the CSS code is going to also like inherit similar properties and also be strong code. So okay, so this suggests an obvious way of getting quantum list decodable codes, which is if you just take C1 and C2 to be classical list decodable codes and CSS them together, and now you get a quadratic blow up in the list size, but it's still going to be like a polynomial list decodable quantum code. So okay, so why does this work? Well, for each potential error on C2, there's L errors on C1. So now in this step one, instead of correcting the errors uniquely, well, you come up with a list of L possible errors that could have happened, then apply the QFT, and now you just have another list of L possible errors. For each error that could have happened on C2, you have L possible errors that could have happened on C1. So in total, you still have L squared possible errors. Okay. So Guruswami and Rudra, as I mentioned before, showed in 2005 that certain folded classical codes can be efficiently list decoded all the way up to the classical singleton bound. So folding is just some operation that we'll get into in a minute, but it has the issue that folding does not produce linear codes anymore. So if you recall from the previous slide, in order to even define the CSS composition of two codes, they both have to be linear, and they have to satisfy more properties, but at the very least they have to be linear. So this folding doesn't appear that it's to be useful, at least at first. And in fact, this is a more general issue. We don't know of any linear codes that can be efficiently list decoded up to the classical singleton bound. Okay, so we seem to be kind of stuck. But let's look at what folding does anyway. So if you take a code word, then what folding does is it basically groups together registers of your code word and then just redefines these as new registers. And then everything really remains the same. So essentially it's like restricting the adversary's behavior. So for example, if you start with a code with six registers, then you fold it, then maybe you'd get a code with 3 registers where each register got a quadratic blow up in size. So now, whereas the adversary before could choose any subset of these 6 registers to attack, now the adversary can only choose subsets of these 3 registers and then has to attack them in sort of bursts together. Okay, so this is what folding is. But notice that folding is like a completely syntactic operation, right? You're really just redefining what a register is. So folding quantum codes is just as well defined as folding classical codes. You could imagine just redefining quantum registers instead of redefining classical registers. So let's just try that. Let's fold a CSS code and then see what happens. And it turns out that if you fold a CSS code, then the result is going to be a code where both of the classical codes sort of look folded from the perspective of your decoding algorithm. Okay, so I have a little graphic to try to illustrate this. So say you have this folded code word, and say errors happen on this first block here. So now, first remember the decoding algorithm for a CSS, or the correction algorithm for a CSS code is to first correct errors in the standard basis here. So we're going to get rid of these errors here. And then we apply the QFT, and then the phase errors show up in the standard basis. So now we can see that maybe there's errors here again. And now we're just going to correct C2 in the same way. So notice that both the correcting C1 and the correcting C2 phases, what we were looking at was just like a folded classical code in the standard basis. So in other words, like from the perspective of these two corrections, we had folded codes. So it follows, and this is one of the main observations, one of the first main observations in our work, is that folded quantum codes work well with CSS codes. So if C1 and C2 are classical codes where the foldings are both highly list decodable, then if you fold the resulting CSS code, you'll get something that's quantum effectively list decodable. So this is even though folding C1 and folding C2 does not result in linear codes. Folding the CSS composition does work and gets you list decoding. Okay. So sort of okay, so we're almost there at this point. This will get you codes that are list decodable up to singleton bound, and then by the same wrapping argument that we had, the wrapping argument that I showed earlier, we can get approximate error correcting codes that are uniquely decodable all the way up to the singleton bound, the quantum singleton bound. But there's still one issue, which is that the alphabet size is going to be polynomial if we instantiate this with like good list decodable classical codes in the CSS code. So this would still be new, but we can do a little better. And the way we do this is we borrow a technique of Alon, Edmonds, and Luby, which is like a classical technique in in coding theory, which is called distance amplification. So what this, it's also sort of a syntactic operation, kind of like folding is, in the sense that you're sort of redefining where registers are, where symbols are. So it's also going to work for sort of similar reasons that the CSS codes work. Of course, showing that it really works is one of the main technical parts of our paper. And applying this technique to our folded quantum codes is how we're going to get our final result. Okay. So a couple of future directions are, for one thing, our alphabet is constant but not binary. So like I said, Leung and Smith construct binary alphabet code, list decodable codes that are not efficient, but the only ways that we sort of know how to take quantum list decoding and boost it to unique decoding require like augmenting the registers with like the secret sharing components. So it would seem to require new ideas to get you all the way down to a binary alphabet. I think it would be an interesting question. Also sort of on the other side, classically, the fact that you can list decode up to the singleton bound ended up being like a really useful fact. I think it's an interesting question of whether anything similar can hold quantumly, where now we don't even need a list, right? Because you can uniquely decode, at least approximately. Okay, so that's all that I wanted to say. So I went a little bit fast, but yeah, I can open the floor to questions, I guess.
Great, thanks, Sam. That was a very nice talk. So, are there any questions? Okay, so barring any questions, maybe we can. Oh, there is a question among the. Here, let me. Okay, go ahead, Victor. Can you ask a question?
So for risk of sounding naive, this was a bit fast for me. Let me just see if I got what I got out of this. You show that approximate codes cannot beat but achieve quantum singleton bound. Approximate quantum error correcting codes cannot beat but achieve the singleton bound in terms of decoding radius. And the codes that you construct are basically CSS codes constructed out of folded Reed-Solomon codes.
Yeah, in some sense, yeah. But I guess sort of that was one thing. You can't CSS folded Reed-Solomon codes together. So you have to fold the CSS code. But that was what I was trying to get across at the end, is that you can fold the CSS code, and then in some sense you end up with two folded Reed-Solomon codes, kind of interestingly. But yeah, exactly. This is the basic idea.
Sorry, yeah. So you had to generalize the machinery of getting a quantum code out of folded Reed-Solomon codes because, and thanks for saying this, I hadn't realized folded Reed-Solomon codes are not linear, so the CSS construction cannot be applied.
Right.
Okay, thanks.
Yeah.
There's no paper, right?
No, it should be out like next week. Yes.
Okay. Yeah. Anand?
Oh, hi. Sorry, I think there's actually a problem with the audio. Okay. Thanks for the nice talk. I think we're just a little confused. Where is the step exactly where you go from being list decodable to unique decodable? I think I sort of missed where that happens.
Yeah, sorry. So that's what this sort of wrapper is. So we have our list. We take our list decoding decodable code, and then we use like sort of this usual trick where you authenticate your message in order to sort of sieve the list down to a unique element. So yeah. Oops.
Is it obvious why that? So the authentication just tells you whether an error has occurred or not.
Yeah, exactly. No, yeah. So okay. So basically, okay, if you authenticate your message and then you encode it in a list code, right? Then now, okay, at least in the classical case, imagine I could just like, list decode and then get out my list of possible corrections. Now I could just go, okay, each of these corrections are like authenticated messages though, like they live in the authenticated space. So now I just check each of them, and only one of them is going to say yes, good, this is like really the right thing, by the security properties of our authenticator.
I see.
Yeah. Maybe I should have talked more about that. Right. So in the quantum setting, of course, now we're not getting the actual list of authenticated states. Now we're getting a list of possible errors, but we show that it actually is okay. Basically, what you can do is like, go through your list of possible corrections one by one, trying them and then checking the authentication, and then trying them and checking the authentication, and then using like a gentle measurement argument to say that you won't destroy your message in the process. Yeah.
Very cool. Okay, thanks. I think that helped a lot.
Yeah, thanks for the question.
Great.
This is a good.
So
question.
Andrew, do you want to ask?
Sure. Thank you for the nice talk. One of the things we say about quantum error correction, that it's important to learn what the errors are, but not learn about the state, because you couldn't encode superposition states. And classically, it's also valuable, not necessarily from a necessary point of view, but from an efficiency point of view to do that. If we have a classical repetition code, for example, it could be more efficient to do syndrome extraction by measuring parity of neighboring bits as opposed to doing a majority vote, measuring them all and doing it that way. And I was wondering if these schemes that you've developed for approximate list decoding for these codes can fold back, to use fold in a different way, to classical decoding to lead to more efficient classical list decoding algorithms or things like that. Is there a way to interpret them that way?
So my inclination is to say probably no, just because I think the main like what we do to me is mostly like, coming up with a way to take like list decodable classical codes and then turn those into list decodable quantum codes. So we're really like using everything we can get out of classical codes to build our quantum codes. Yeah.
So sometimes you can think of, for example, stabilizer codes as like additive codes over, GF whatever, if you're doing not just using, qubits. And I didn't know if there was any value, a way to think about these codes as classical additive codes, say.
Yeah, not that I know of. I don't know. I'm not sure though. Yeah. So I guess one other thing is where I thought you were going at first was classically, quantumly, there's like as you said, there's this requirement that you have like this local indistinguishability property, right? Whereas that's not true classically at all. So that's kind of exactly what these robust secret sharing schemes are asking for, though, right? It's like robust secret sharing schemes are like saying, okay, well, if you think of quantum error correction instead as requiring both error tolerance and like secrecy against local views, then like then robust secret sharing is like the right analogous thing to quantum error correction. And interestingly, actually, this robust secret sharing schemes are subject to something more similar to the quantum column here, the quantum columns here in in terms of upper bounds. So yeah, I don't know if that might not be related to what you're asking that much, but
no, but that was interesting as well. Yeah, now I was thinking if there was a way for it to give back to classical codes at all, if there was a kind of sort of a
definitely. Yeah, I guess it's for that thing. I think I guess I would. The reason why my inclination to say no is just because like our work is all, the work for us is all about like taking existing classical things and then figuring out how to like look at them in the right way to get a quantum thing out of it. But so it's maybe you could do something like that, but it's not clear to me.
Right. Yeah, I wasn't thinking you'd get any improvements in terms of limits of these rates and things like that, but maybe just getting up to like this half rate that you could get to classically, you might be able to use more efficient simpler decoding circuitry, which can be very practical for classical codes.
Yeah. Yeah.
Okay. Well, thank you.
Yeah. Thanks.
Okay, let's see if there. So one other thing I think in terms of the list decoding, quantum list decoding code that you define, that's not approximate, right? The approximation comes in the envelope, is it?
Yes. Yeah. Exactly. Yeah. The approximation comes in here when we from the authenticator and the robust secret sharing scheme.
Great. Yeah.
So yeah, you can list decode exactly. Yeah.
Are there any other questions? Oh, there's a question. Let me just.
I think Chinmay has a question too.
Oh, Chinmay, do you want to go ahead while I figure out?
Yeah. Hey, Sam.
Hey.
Can you tell me a little bit about what the logical bit flips and phase flips look like for this code? Because and I'm sort of missing how those connect to like the distance radius. So maybe if you could elucidate a little on what those look like.
On the bit flips and phase.
Like if I was to encode something and then I wanted to apply like a logical bit flip, what would that look like? What does that unitary transformation look like?
Like a logical bit flip?
Yeah.
Yeah. That's a good question. I think it would correspond to some Pauli, but I think it's not clear what exactly it would correspond to, especially because if you want to, so are you talking about the list codes or the final approximate codes?
The final.
Yeah. So with the final approximate codes, right, because there's this like authentication going on, you would really have to like, it seems like it would be something kind of complicated. Like you have to apply some logical operation that like does something on the space on the like code space of both the code and like the authentication space. If that makes any sense.
So the thing that sort of confused me, and maybe I'm just missing something elementary, is I thought if the logical operation was a Pauli, then I could sort of imagine someone going term by term by term, applying terms of the Paulis, and eventually he'll get from one logical state to another logical state, right? If he applies enough Paulis, like he gets further and further, and then he comes back down. But somewhere at the halfway point, if the operation's a Pauli, he should switch from answering state 1 to answering state 2, right?
Right.
But then that seems in tension with the distance, the radius being, like near the bound here. So I was sort of confused by this. Maybe you can say a few things.
Let's see. Let me see if I can understand the question and think of a good response. Also, it looks like, I don't know if Louis, if you have any thoughts on this, also feel free to weigh in.
Yeah, I was just gonna, as to like the first thing you asked, I think, so the codes we end up getting are basically like a classical ensemble of stabilizer codes. So the logical operation, I think, would be if you have the secret key, you know which of these stabilizer codes you're in. So you can just apply like the logical operations for that stabilizer code. I'm not sure if that answered.
So I guess when okay, so you're saying that that this view of like applying Pauli's one by one is like you know, so seems like it's you know, would fit into this picture, but you're saying that it doesn't seem consistent with the fact that that you have decoding radius all the way up to the distance, something like this.
Yeah, exactly. Yeah.
So maybe, I'm not sure, but maybe one way to reconcile these things is that your approximate thing comes from the ensemble average after you average the keys. And so this intuition that certainly if you sort of fix a key at some point, you will cross over to a different logical state, but somehow the way that happens is very different for different keys. So when you average, so because you do these polys without knowing which key it was, like if you're trying to convert one state to the other, you don't know the key. So since you don't know the key for most keys, you will be actually going to a place where you started with is the only correct place. So, but there would be, but if you knew the key, you can certainly go to
The midpoint,
yeah. Well, I think
I think that's right. I think what you need to do is, if you don't know the key, you need to look at enough registers so that you can extract the key from the secret sharing. And then once you know it, then you can do the right thing. But that's like a many qubit or many qubit operation. And so if you're just guessing, then yes, you'll go off and you'll get something wrong and it'll just be clearly wrong and you can be corrected. But if you have enough, then you can look at them all together, find the right key, and then you can do the right thing.
Thanks.
Yeah, thanks. I think that seems like definitely the right answer to me.
That's great. Victor, did you still have a question, or
No,
your hand's still up? Oh, okay, good. Great. Well, that was a very nice. Both a very nicely done talk. You know, very nicely dissected set of ideas and great questions. So now, maybe if you stop sharing your slides, we can move to the panel. So we have a great panel today. Debbie Leung from University of Waterloo, who, as you already know, was very appropriate for this panel. She defined quantum list decoding codes in addition to all her work on fault tolerance and cryptography and so on. And of course we have Venkat, who I think well, he's first of all one of the senior fellows at the Quantum Institute, but he's also played a pivotal role in defining quantum classical list decoding and the best codes there, and lots of other stuff. So Venkat, and then we have Steve Flammia on the panel, who's now at AWS, and he brings a much more of a physics sensibility to this subject. He's worked on condensed matter theory, topological phases, and of course error correction, tensor networks. So really a great panel. I wonder if we can, if there's somebody who's pinning the videos of the panelists. Sorry, do we have?
They're pinned. The videos are pinned.
Oh, are they? How come I'm not seeing them? So is everybody else seeing them pinned?
They look good to me.
Okay, great. So maybe could we just start with comments from Debbie? Would you like to start?
Sure. I have some questions on the result still. I think the first is what happened to the key size? Because if you need to authenticate the symbols, the authentication key has to be, the symbols themselves have to be encrypted by a classical key. There is a result by Daniel and others that in order to authenticate a quantum message, you have to encrypt. So there seems to be a lower bound on the key size. And then when you have to perform secret sharing, robust secret sharing on the keys, it seems to run up your symbol size by a certain amount. So it would be nice to see a little detail on that. The second question is that following up on the discussion earlier about knowing the key and knowing what code you have, and therefore you can try to perform a logical Pauli by running the symbols or running on a physical Pauli one by one. If you use classical key, is there some notion at which the adversary can look at the key without changing them, and then using the key to defeat your result? Because then the adversary may have some idea what random code is being used. Again, sorry, I may have missed some of the detail, how it actually work out.
That's good. Wait, so you're saying if the adversary learns something about the keys, then they could use this to defeat the code?
Yeah, I'm a little confused about the fact that the key are classical and somehow it is. Is it sent in the open, or is it also encrypted? Encoded as a quantum message?
Sorry, so that's the point of the robust secret sharing scheme. So the robust secret sharing scheme is there to hide the key from the adversary while still transmitting it to the receiver. So the robust secret sharing scheme has this property that as long as the adversary doesn't look at too many registers, the key looks completely random from their point of view. And furthermore, whatever they do whatever adversarial attack they do, the recipient, given the whole message, will still be able to recover the right keys with high probability.
In that case, it seems to imply that the corruption model is that the adversary cannot even look at the message.
Yes, the adversary cannot even look at, which is necessary in the quantum setting, because if you can sort of look at if the adversary could look at the entire quantum message, then they could measure it and like collapse it, right? So yeah.
So you have encrypted the classical key as a quantum message.
Yeah, you could think of it that way. Yeah. Right. Yeah, I think you're bringing up a really good point. There is a kind of a bit of like a modeling mismatch, I think, between classical error correction and quantum error correction, which is that a lot of times classically you think of the adversary as looking at the whole message and then perturbing only part of it, whereas quantumly, in some sense, it doesn't really make sense to look at the whole message, right? Because if the adversary could actually like measure the whole message, then they would destroy it. Yeah. So we're assuming that the adversary can only look at a small fraction of the message.
And then what happened to the key size?
Oh yeah, okay. And then the key size. So I think that the reason is the answer to your question is that mainly because we use these things called purity testing codes, which are like slightly different than message authentication codes. Basically, like we're able to reduce to the case where like sort of only Paulis are happening. and it turns out that you can build like very efficient purity testing codes, and right. So it ends up that the keys won't actually be too large.
Yeah, the confusion comes from the fact that the authentication code by Cropole and Barnum, Cropole, Gottesman, Smith and Tapp, has the feature that you use the purity test code as a middle step.
Yeah.
And in the end, there is still it only counts for a small portion of the key.
Yeah.
There is a part of the key that's twice the message length, the quantum message length, and then that can be recycled. So the overall use is small, but the initial key is actually big. I just wonder how you get around that problem.
Yeah, or so if I'm I might be misunderstanding, but so we only use the purity testing part. We don't need to like fully authenticate. So this is why I put authentication in quotes, just because it's like morally it's something like authentication, but really the purity testing code was the only thing that we use. So in some sense, like the code around it, like the list decodable code around it, takes care of the other takes care of the other issues, I guess.
Okay, thanks.
Does that? Yeah, I don't know if that helps. Also, Tiago and Lou might have if you guys have any thoughts on this question, I might be missing something. But I don't know. Does that answer your question? Right.
So I might also be able to later comment on some connections of this to the classical thing. So I mean, this particular part on how you interface, how you get a unique decodable thing out of list decoding. There are some classical analogs of that too in restricted models. And
do you want to go ahead, Venkat, and do it now? Give your comments now.
Sure. Yeah. So I guess there is this question of how do you interface this list decodable thing with this authentication. And I must say in the quantum setting, I'm also a bit fuzzy on that, but because it's I guess things are more subtle in this thing. But in the classical case, you can have this model where you do a randomized encoding of the message, and the adversary is allowed to see the message, but not the internal randomness you use to encode. So it doesn't see the code word, but sees the message, and the message goes to a distribution of code words. And in this case, one can reduce list decoding to unique decoding. And essentially the idea is something similar. You use some sort of an authentication code, some specific form. And in fact, one thing which works nicely is that if you use a linear code, then the set of possible errors does not depend on the set of possible offsets of the message only depend on the error cost. So because of this, you sort of break some dependence, and in some sense, you only need this authentication to be good for some fixed number of offsets, which you can build just without any crypto tools or anything. It's a purely sort of information theoretic fact that you can build such authentication codes for such algebraic manipulations. Essentially, you don't allow arbitrary distortions, you allow some linear operations. And so then you can essentially do the same thing. You can take a random key, apply this thing, which I think is called an algebraic manipulation detection code. It's used in some crypto settings, AMD. So you just apply this AMD code, you do list decoding, and only one of the offsets will match with high probability. So you'll get your unique decoding. But of course, the key thing here is that you restrict the adversary to make the errors before seeing the full code word. Right. So in the classical setting, it makes sense for the adversary to see the full code word, but you disallow that. The errors have to be picked before, independent of the randomness in the encoder, which is somewhat reasonable model and the randomness need not be shared with the recipient or anything. It's completely local to the encoder. So there is that connection. Yeah. And actually, in this context, I had a sort of a question, or more like a just thinking out loud, is that in the classical case, we don't know so one way to get binary codes which achieve this optimal trade-off would be to take a binary list decodable code, apply this thing which I just said, this sort of AMD trick, and you will immediately get uniquely decodable codes in this somewhat restricted but still reasonable model. And I was wondering if, you mentioned some obstacles in getting an analogous result for binary, qubit codes. So if you did have your dream list decodable code in the binary world, then is there something one could do? So that was just something I thought we could discuss. Yeah, maybe it doesn't have a clean answer, but yeah.
Okay, yeah, that's a good question. Yeah, like suppose you had your dream binary list decodable code, to whatever limit you can do that to. Yeah, I mean, I guess the thing is you can't do this robust secret sharing trick, right? Because that's going to blow up the alphabet. So yeah, it seems to me like the only thing that you could do off the bat would be, relax your model and say you're allowed like a side channel. But I think it was a really good question of whether, and I think, and someone even suggested to me maybe one possibility of doing this recently. But I think it's an interesting question of how you might do this without, relaxing the model or having increasing the alphabet size. But somehow you have to so I mean, okay, maybe like the obvious, maybe the most direct thing to try would be to something like somehow you still have to hide your keys in other qubits. Maybe you could put the keys in more qubits and just lengthen the code and then somehow scramble them so that you don't know where they are. But I don't know if something that can be made to work. I haven't really thought about it yet.
There were also a couple of other things I was intrigued by giving back to classical, but I think we can come back to that. Maybe, maybe Steve wants to say something. So.
There's just been a ton of discussion. I'm not sure I have that much to add, actually. I do have a question, though. Is it known that you need to expand the alphabet to apply these robust secret sharing schemes? Is that necessary? Or known to be necessary?
So I guess what is necessary is you need to expand the alphabet somewhat. Like the closer you want to get to the Singleton bound, you need to expand the alphabet. The exact trade-off, though, we haven't pinned down yet.
I see.
Yes, there's also, I guess there's also the same thing kind of holds with robust secret sharing. So I think if that's what you're asking, like robust secret sharing.
I see. So it's independent of whether or not you use that specific scheme, which does expand the alphabet. Yes. It's just it's separately known that you have to blow up the alphabet size a little bit, but it's not known what the bounds are.
Yeah, exactly. So you have to blow up the alphabet size in order to get closer to the quantum Singleton bound, definitely. Yeah. So I guess the question is, okay, if you fix yourself to qubit alphabets, for instance, then there's some it's not the quantum Singleton bound, there's some bound you can reach. Yeah, the question is kind of what is it, I guess. But yeah.
And your current best parameters scaled they were exponential in the distance to 1 minus r over 2.
Yeah, exactly. Yeah, exactly.
Okay.
Yeah.
So yeah, it would be nice to improve that, I guess. There's nothing known about how that should scale.
Okay, so it's a really good question. I think I mean, maybe I shouldn't claim this yet, but I think if you do, there's some heuristic kind of arguments you can make that make it seem like actually that's necessary. I don't think that it's actually known that you need it to grow exponential and the alphabet to grow exponential and 1 over the slack, but I'm pretty sure that's a necessity. Yeah.
What's the argument for that?
It's actually something, basically another argument like this no cloning, this no cloning one that I gave on that third slide. Let's see.
A quick comment there is that for the list decoding itself, you do need the alphabet to be exponential in this 1 over gamma. But of course, you might build these quantum things without relying on list decoding. So at least the way they are approaching it by starting with list decoding right off the bat, I think you do face this big blow up. And that is purely just an information theory sort of counting argument that you need.
I see. Okay.
But it doesn't have to be exponential in 1 over gamma to the 5. It only, I think, has to be exponential in 1 over gamma. So there's definitely something loose there, but the high level trade-off that you should really think of it as the number of bits in the alphabet, and that has to be 1 over gamma. I think that comes for some information theory reason. Now for the approximate error correction, I don't know. And it will be actually quite interesting if there is a separation. So
interesting. Okay, yeah, thanks. I didn't realize that was true for list decoding, but that's yeah.
Anything else? But Debbie, did you have more to say? Or anyone else?
Yes, it is awkward for me to ask a question about my own result. But then how did we get around the problem not expanding the binary alphabet? We didn't get close to the singleton bound. And we did not even get close to the rings bound. 0.3 something times the number of qubits that we send. And we use a key, which is logarithmic in the block length, and we can sneak the key into the transmission to regenerate it. And we do not know whether that is necessary at all. In the classical setting, if you try to do the same for a binary classical binary adversarial channel, and you try to use list decoding and you try to approach a similar bound, we learned that it seems to be necessary to use some key. So I get a little curious how these all come together.
Yeah. So maybe if you don't have, sorry, did you want to answer Debbie's question, or did you have some thoughts to share, Sam?
No.
Since I was given the role of the token physicist, maybe I'll try to ask a bit of a physicsy question, or just maybe motivate some thinking along some physicsy lines. There's really kind of two local dimensions for subsystems that people like to think about, and one of them is 2. But I guess we're not going to get very close to the singleton bound if we're stuck at 2, apparently. But the other is infinity. And that's because there are these beautiful codes called bosonic codes. And the mathematics of these is quite different because you're encoding in a system that has ostensibly an infinite number of levels. What you do physically instead to make this reasonable is you put some kind of energy constraint or something so that you can't access all of these levels. But I'm wondering if there are ways to derive some results that exploit these types of codes directly. I mean, I realize this is a theoretical result, and we're not about to implement these codes in the next few days or weeks or probably years. But I think it would be extremely interesting if they were made to be a little bit more native by exploiting some inner codes that were bosonic codes. I think the reason I think this is interesting is because people are actually trying to build these codes, and they've been quite successful. There have been experiments recently where people have shown that if you take an oscillator and you encode a qubit into that oscillator, then the qubit can have a lower logical error rate than the bare error rates of the oscillator in a specific sense. So this isn't quite the same as an error correction experiment where you take n qubits and get out k qubits, but it's morally very similar, and it's also technically extremely challenging. And if you can use this to get better qubits, you can concatenate into a code as well. So yeah, I mean, I wanted to just maybe motivate the idea that it's worth thinking about large alphabets, but that the physical way to try to do so is to think of those alphabets as embedding into some harmonic oscillator, or some sort of physical system that has that natively contains all of these levels. And people have thought a lot about these codes. I'm not sure if it's possible to weave your arguments together with some of these things directly, but it seems to me like it's something worth thinking about. More of a comment than a question.
Oh yeah, that's a really interesting point. I wasn't aware of these bosonic codes really. I guess on a related note, I know that Louis has been thinking a lot about making these codes that we've constructed LEPC, using these similar. I guess it's kind of a related thing of like, you know, how physically implementable is it? Seems like there's some promising stuff there.
Yeah, I was going to ask that too, actually, that if you can, instead of using CSS codes, I mean, it seems to work for general CSS codes, right? But I didn't follow all the constraints that are on them, but these balanced product codes and things like this are CSS. So it may be possible to improve some of the performance with respect to the weight of the stabilizers of the code.
Yeah, definitely.
Mm-hmm. Great. Anyone else have comments?
So just one quick point, since I think it was Andrew who asked about whether this can give back to classical things. So I guess even in classical, one can imagine asking an approximate error correction question where it'll only make sense for, say, big fields or something. But you could imagine, big prime field, and you could allow some sort of like L infinity error. So you could sort of make a mistake in every position, but then you make some sort of bounded error. And that seems to be the flavor of what you're getting at, because because if you of course make a small number of Hamming errors, you can of course correct it with just a pre-code. So that cannot be done in the classical case. But if you allow more continuous errors, like some L infinity error or something, so do you have a sense of whether and also at a sort of a higher level, I was wondering how much one can sort of black box from classical coding to approximate QEC in this thing, right? So in the sense that, is it just list decoding plus this? Or, I mean, how much, to the sense that, I mean, one of the powerful things with the CSS framework was that it told you exactly what you needed in the classical thing and you're done.
Yeah.
And which is also good because it allows you to then inspect it and change it, and which exactly as you guys did the folded version, etc. So I'm sort of wondering, of course, it's still early days after this result, but it'll be nice to introspect and see how much one can model array some of these components, right? So to see where it is.
Yeah, that's a really good point, really good question. I think
no, go ahead.
Yeah, I was just going to say. So I think for the most part, it's very black box. Okay, so we technically, for the last step to get constant alphabet size, we're going to require some like list recoverability property. But I think for the most part, I think it's like you should be able to very much like black box away. Like whether it's Reed Solomon or some other code, I don't think it should matter very much.
Maybe
there are a lot of restrictions though. It's like it has to be, it has to be linear, and then it has to have list decoding.
I guess
it sounded like go ahead, Venkat.
No, I'm just finish this thought, Umesh, and then I would love to hear what your comment. So maybe I want to say that the question is also where you modularize, right? I mean, of course, I'm happy that you make list decoding a key black box, but I wonder whether it should really be some form of approximate classical error correction in the unique world, and say that if you have this, then you get quantum, and then you kind of build that using list decoding, perhaps, or maybe not. So I'm also thinking whether you could, for example, solve this approximate error correction problem with, say, L infinity error up to the singleton bound uniquely, right? In the classical world, whether that could, maybe that's the right level of abstraction. Kind of then pass to the quantum. I mean, I don't know. I'm just wondering. So.
Yeah, no, I think I get it. I think that's a good point. I think also another alternative potential sort of like classical analog is this robust secret sharing thing. So I think I mentioned earlier, robust secret sharing seems to be subject to similar bounds as approximate quantum codes. So I think it seems plausible to me that, you know, maybe there's some way to, rather than doing our like list decoding and authentication construction, maybe you could just take robust secret sharing, classical robust secret sharing, and directly get approximate quantum error correction out of it. So maybe it'd be a related thing to try, but I wasn't able to make it work. So yeah.
Okay. Sorry, Victor seems to have a comment again. Do you want to go ahead and ask your question?
Yeah, I just want to butt in and piggyback off of Steve's comment about bosonic codes. Bosonic codes, stabilizer codes, are based off of lattices and hyperplanes in Rn. So the stuff you guys want to do on the classical side, like folding and list decoding, should probably be looked at in Rn, and maybe it already has. I just don't know, but that would be a step probably toward making quantum versions of these things.
Okay. I guess before we end, Andrew had a question that he put in the chat before he had to leave, which asks, you know, where he asks about XYZ product codes, which I didn't know about, so maybe one of you does, with generalized CSS codes by combining 3 classical codes. And he asks whether those can be folded in sequence in some way and also generate approximate quantum codes that saturate the quantum singleton bound. So maybe my first question would be, does anybody here know about XYZ codes and what they are? Because I don't. And
I think Anthony Leverrier is on this call, and I think he's an author of this paper. Maybe he wants to say something.
Anthony, are you?
Maybe he's too shy.
I don't. Oh yeah, he's here. Okay.
Yeah, I mean,
Maybe
I guess. I guess the point is that, you know, you can imagine correcting X errors and Z errors separately with a standard CSS type construction. But you might want to consider correcting Y errors. And of course, conceptually, these are redundant because X times Z gives you Y. But the reason you might want to correct them separately is because maybe your Pauli channel has some bias. And this happens actually in a lot of physical architectures. Some error rates are biased towards some errors rather than others. So you can kind of symmetrize over the Pauli algebra a little bit. When you correct Y as being a product of X and Z, you're kind of morally hoping that the Y errors occur. Like conceptually, what's happening is you're saying an X error with probability P and a Z error with probability P combine to give you a Y error. But the way you would, but then you're sort of implicitly asking it to occur with probability P squared. You don't have to, of course, your decoder, you could try to tune your decoder or something, but these codes try to symmetrize the Pauli algebra a little bit better, or to give you more finer grained control over how the power to correct X versus Y versus Z is distributed throughout the code. So I think that's a motivating reason to consider these codes. So it's like giving you one more thing to fold into the product construction. And if Anthony were here, well, he's here, but maybe he stepped away, or maybe he's too shy, he could tell us all about these and whether it would work, but he's not here, so.
Okay. Tiago, did you have something to say?
Yeah, I had a quick question. So the the techniques in this paper, they allow us to ask an analogous question of list decoding from erasures, even for quantum codes and very small, even binary alphabets. And this is something that Venkat has done extensive work in a classical context, but I did want to more generally ask about different types of error models, whether say with biased noise or just not strictly restricting to erasures and adversarial errors. And I was wondering whether you guys have any ideas, or the panelists have any ideas about how these techniques or related techniques could be used for, say, if you knew that X errors occurred with some biased probability.
Any thoughts? Sounds like a pretty big question to ask, right? So,
I mean, my initial reaction is, I mean, just the obvious one, which you all know, which is that, of course, these two codes correct different numbers of X and Y, Z errors, right? So at least if you knew X errors are more likely, then maybe you can pick one of the codes in a more skewed way, so that DX is higher than DY or DZ or something. Yeah. But otherwise, I mean, I don't have a more thoughtful answer than that. So.
Actually, is that if you had that static case, is that the optimal thing to do, or is there something even better you can do? Is that known? What you suggested sounds like.
I mean, it'll be the first thing you would suggest, but it probably might not be the right thing. I mean, often is not in these cases, right? So,
yeah.
And there was also a related thing which correcting Y errors. Like somehow when you only correct X errors and Z errors, you kind of pay some factor 2 or something if you want to correct all errors on up to E bits or something. Like you need to be able to correct both EX errors and Z errors sort of simultaneously. And maybe the discrepancy is because of this Y, and maybe this XYZ codes address that. I mean, I'm curious. I'll look them up, but I'd never heard of them before. So.
My main concern is that an error model like this is not very adversarial at all. You have to trust that indeed there is largely X error versus Z error. And that seems to walk away from the whole spirit of trying to cope with as much adversarial error as possible when we talk about error correcting codes, rather than, say, channel coding.
Yeah. But I remember there was one talk in this Colloquium series, maybe 6 months ago or something, I forget the title, I'm sorry, which actually said that in some physical implementations, it seems erasures are more likely, is what is happening. So it sort of gave some renewed interest into erasure codes. So I guess to the extent that you want the models to reflect the current physical implementation, and there seems to be a wide variety of this based on which implementation people are talking about, right? So since it's still all developing, so there's I think more possibility for dialogue between the specific implementation and the model one should think about than, say, in the classical case where it seems relatively well trodden that you have 3 or 4 models.
Most likely you have a bunch of erasures, and then there are some also unknown errors around.
Great. Well, if there are no other comments, maybe thank you. Thanks, Sam. For
I want to add one more comment.
Yeah, please go ahead.
Steve have already walked away. At least the in-house physicist here. But there is a whole community of people also working on something very similar in title called Approximate error correction, in which case they look at one specific error correcting code, but it satisfies the error correction criterion approximately. Because the quantum error is continuous. And so you can define these notions, and you can talk about a lot of different scenarios in which you fix one code, but the correction is approximate for all sorts of reasons. It looks very different from the kind of approximation study here in the more cryptographic setting, when the approximation comes from the randomness in the code chosen. I do wonder if there is, it looks very different. So upfront, there seem to be two slightly different subjects. I do wonder, is anyone having different thought that this can be more connected than what it looks on surface?
Yeah, that's a good question. I'm also not very familiar with this other sort of line of work, but I think I had the same impression as you did, that they sort of have different goals in mind. So like usually these codes, what I was seeing, it looked like these codes usually have distance that's like logarithmic or something in your block length, if I understood correctly. I guess it's like they were interested in questions like, you know, what would a natural, like exist, like naturalizing code, what kind of approximate error correction properties would it have, as opposed to us, which is like constructing an approximate error correction code with the best properties you can get. This is what it seemed like.
Okay. Well, and for, you know, it's a really good question. I don't know if we have the expertise on right here to resolve the question. So maybe good question to bring up, and we can explore it offline. Okay. Well. Okay. So is there anything else you'd like to discuss before we call it a day? Otherwise, thanks, Sam, for a great talk, and thanks to the panelists for the comments, and thank you all for showing up, even though you're missing a World Cup match. But you know, next week, next Tuesday is the semifinals, and that's, you know, we can't, you know, we can deal with this round, but not with the semifinals. So there's no colloquium next week. And then since that was going to be the final colloquium, that's it for this semester. So great to see you all, and we'll meet again next semester.
Thanks.
Okay, great. Right, bye.